Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, we are going to discuss about register files unit in our RISC-V process. Basically, this is a very important file unit which we need to know, like what are the different kind of registers do we have and what is the role of each and every particular register. So basically, in our RISC-V processor design, we are going to have total 32 general purpose registers and one program counter we are going to use. Now let us try to understand what are those particular registers, and this particular session agenda is we are going to discuss about register file overview, and we are going to discuss X0 register. We are going to discuss about different kind of pointers like stack pointer, global pointer and thread pointer, and the written address register and temporary registers, saved registers and argument registers and program counters. So these are the different kind of register categories which we are going to discuss in this particular session. Now, basically, in our RISC-V processor, we are going to have 32 general purpose registers starting from X0 to X31, where the size of each particular register is 32-bit. And if we are basically using RV32, RISC-V 32. Now, there are basically two read ports, RS1 and RS2, and one write port matching how ID reads and write back write every cycle. So, what does this mean when we are going to discuss about instruction set architecture? It will be clear. Now, whereas the very first register, which is X0, is always hardwired to 0, and you cannot write anything to that particular register. And if you are going to read it any particular value from that particular register, you are going to get 0 itself. Now, so that is what I was saying about in the previous slide. So basically, X0 register is basically a zero register which is hardwired to constant zero, and it is not going to store any particular data. And any read operation which is basically performed on this particular register, I'm going to get written value as zero regardless of what was written before. And any write to X0 is silently we are going to basically discard it, and I'm not going to have any effect on my machine. And this is basically used in my pseudo instructions. So this is about the first register, which is nothing but my X0 register. Now, before going to discuss other registers, we need to understand this concept of memory configuration. Okay. Now, what is this memory configuration or memory layout? So basically, we are not going to use an entire memory as it is. Like we are not going to store the program. We are not going to store all the particular code and all the particular variables, everything into random locations. No, we are not going to do that. So basically, memory is classified into these categories, whereas the higher address is going to have command or line arguments and environment variables present. And then after we are going to have stack, then heap, and between the stack and heap, we are going to have an empty space, and we are going to have other kind of section which is known as static memory layout. So basically, the entire memory will be divided into two types, basically three types. One is static memory layout, next is dynamic memory layout, and another is command line arguments. Okay. Now let us try to understand what do you mean by static memory layout, what do you mean by text segment, initialized data, what do you mean by dynamic memory layout, and all. Now, coming to static memory layout, as the name itself suggests, basically this particular layout contains sections whose size is determined before the program is going to start executing. Okay, so as the name itself suggests, static is nothing but it is not going to change. Okay, so whatever the variables we feel, those particular variables, if we are not going to change the size during the execution of my program, those particular variables I'm going to store it in my static memory layout. Okay, and this particular static memory layout is going to contain text segments, initialized data, BSS, uninitialized data. Okay, and these particular sections are not going to continuously grow or continuously shrink while the program is going to run. Okay, let us try to understand it more clearly what is it means. Now, before going to understand about this static memory layout and text segment and all, let's first see about a brief intro about dynamic memory layout also. As the name itself suggests, it's basically dynamic in nature. That means this particular dynamic memory layout is going to change while the program is going to run. Okay, and this we are going to use something known as heap and stack in this particular dynamic memory layout region, and these particular regions are going to grow and shrink depending upon the program's behavior. So these are the two categories we are going to have. One is static memory layout and dynamic memory layout. And let us try to understand what exactly which is being stored inside this particular static memory layout, and what is this particular different kind of sections we are going to have in my static memory layout. Now, first of all, in the static memory layout, the first segment which I'm going to have is text segment. So this is the first region we are going to have in my static memory layout. That is nothing but my text segment. Now, what do I mean by this particular text segment and what is it basically storing is this particular segment is basically is the first section in our memory, and it is going to contain executable machine instructions generated by the compiler. So whatever the compiler is going to compile and whatever the compiler is going to convert that particular code which we have written into machine instructions, right? So those particular instructions will be stored in the memory segment which is known as text segment. Over here, whatever the machine level language code or the instructions which were there, right, which will be stored over here in this particular section which is known as text segment. Okay. Now, so you can see this particular code. So we have written this particular code. After compilation, compiler has generated a particular machine level code, and that particular machine level code will be stored inside this particular text segment. Now, this particular text segment is going to contain machine instructions, it is going to contain functions, program entry points, and interrupt service routines. And what is the characteristics of this particular text segment is it is only read only, and it is executable, and it is not going to change during the execution, and it is basically loaded from an executable file. And who is going to access this particular text segment? Our special counter or our special register, which is nothing but my program counter, can access this particular text segment, and it is going to basically fetch one by one instructions from this particular segment of memory. So in this whole segment of memory, I'm going to use this particular text segment, this memory, this lower addresses I'm going to allocate for my instructions to be storing. Okay. Next I'm going to have something known as initialized data segment. So after the text segment, next set of addresses we are going to allocate for my initialized data segment. So I'm going to allocate a part of memory to this particular segment, which is known as initialized data segment, where it is going to contain all the particular initialized data. For example, if I'm going to declare any in my code, if I'm going to declare int counter is equal to 10 or character grade is equal to 8, during the declaration itself I've basically initialized these values also. So where are these particular values are being stored? These are basically stored inside the segment which is known as initialized data segment. So that is what it is written over here. So we are going to basically store all the global variables with initial values, and we are also going to store the static variables with initial values declared, and we are going to also read or write from the memory, and whatever it is going to exist throughout the program execution. Okay. So these are the values which we are going to store inside my data segment which is known as initialized data segment. Next is BSS segment. So basically, BSS stands for block started by symbol, and this particular segment is going to contain uninitialized variables. For example, if I'm going to write down int count and static int total, like this, I've declared particular variable. Now, where is the memory allocated for this particular uninitialized variables? So in the BSS segment, those particular memory will be allocated for this particular uninitialized variables. So here, the compiler is not going to store a large block of zeros in the executable, and it is only going to basically reserve 4 bytes for count and 4 bytes for total. So it is basically going to allocate this particular memory inside this BSS. So when the program starts, the operating system is going to automatically initialize this memory to 0, and we are going to have count will be equal to 0 before our main is going to execute. Okay, so this is how we are going to use BSS segment. And if you carefully observe, here the size is fixed. You cannot change the size of this variables during the runtime. Or here also the size is fixed. You cannot change the size of this during the runtime. And this whatever the instructions in the text segment, after fetching the instructions, that's it. If the program starts, you cannot after the program starts, you're not going to add some more instructions, right? So this and all will be fixed. So that's the reason these are being fixed, or these are being allocated in a layout or the data segment which is known as static memory layout, where we are going to have text segment, initialized data, and uninitialized data, which is nothing but my BSS. Next coming to the other kind of memory layout, which is nothing but my dynamic memory layout. Now, what is it we are going to have in my dynamic memory layout? Let us try to understand. Now, in the case of my dynamic memory layout, I'm going to have something known as heap. Now, so heap is basically used for dynamic memory allocation. So if you want to dynamically allocate the size of a particular variable or the number of bits to a particular variable, you are going to use a memory region which is known as heap, where the compiler is not going to know the required memory size until the runtime. Okay, so during the runtime only, my compiler is going to know the size of whatever the variable we are going to have, which we are going to declare as a dynamic variable. In system verilog also, we have seen this particular kind of dynamic arrays. So the memory manager is going to allocate space from this particular heap, and whatever the heap characteristics are, you are going to allocate the memory during the runtime. It is basically going to have the dynamic size, and it is going to grow upward. Heap is going to grow upward, and it can basically grow or it can basically shrink. Now, what do I mean by increasing upward is, so you're going to allocate the memory locations from down to up like this. Let me show you. So you're going to allocate the memory locations from down to up. So heap is going to grow from down to up, and stack is going to grow from top to bottom. So the memory locations will be given from top to bottom, and there will be some memory free space available over here, which heap can utilize as well as my stack can also utilize. Okay, so up to certain point, they can be utilizing, and at a particular point, if they are going to conflict with each other, then we are going to get errors over there. So we need to use it where at a particular point where stack and heap can grow simultaneously. So where this particular heap is going to contain this kind of dynamic memory allocations. And who is going to manage this particular heap? We are going to C runtime library or operating system or memory allocator. So this is this is where we are going to use our heap. Next, we are going to have the free memory, as I said you, which is being basically present between our heap and the stack. And initially, stack and heap are going to use this particular free memory. And in the free memory, nothing is basically stored in over here, and it is going to act as a buffer, which is going to allow both the heap and the stack to exist. Next, as I already told you that what is going to happen if heap and stack is going to meet, then no free memory remains, and the possible consequences are heap allocation failures or stack overflow, and we can also have undefined behavior if memory regions overlap. Next is stack. Now, what is this particular stack? So basically, the stack stores temporary information for function execution. For example, if I'm going to have a function, void function, and I'm going to have an internal variable which is being declared inside my function as int x. Now, where is the memory, or how the memory for this particular local variable? And if you have known already, the local variables which we are going to declare inside my function are basically going to have temporary memory storage. So that particular temporary memory storage will be allocated in my stack. And when the function is going to return any value, the memory which was allocated to this particular local variable is going to disappear automatically. So this is where you can think of using a stack. And stack is going to store local variables, whatever the local variables inside your function you're going to declare at those particular variables. And also it is going to store the written addresses. It is going to store the saved registers. About the saved registers we are going to discuss in a little bit upcoming slides. And next, it is also going to store function parameters and temporary values. And the heap is going to grow upward, and the stack is going to grow downward, and this allows maximum utilization of available RAM. So this is why we are going to basically have this growing directions in opposite directions of my stack and heap. And I'm going to have a stack pointer. So what is meant by stack pointer? Let us try to understand. So first of all, before going to discuss about any other registers, I wanted to discuss about this memory organization in detail, so that whenever we are discussing about stack pointer or global pointer, we will be clear like how we are actually utilizing the memory, and where is the code is being actually stored and all. Yes. So that's about this particular session. And in our next session, we are going to continue with our discussion with what are the other kind of registers which we are going to have and what are the role of each and every register. Yes. So that's about this particular session. So if you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.